talk a little bit about the project one optimization that we haven't talked yet. Yeah, so recall there was recall there was a problem of coalescing, right? You have a header and footer. So by the way, this is an optimization that you don't need to implement right away, but only, I guess, once you get once you get an explicit list, maybe hopefully segregated list already, and then you decide to get more points. And even if you implement segregated list, you won't get 100% points. And the reason for this internal fragmentation. So we are wasting too much space for headers and footers. So we have header, footer, and the payload, right? So in terms of header, I guess it's really hard to get rid of the header because header has to give the size. When we call free, we need to know the size of the block at the very least. So we cannot really get rid of the header. And header is also used for coalescing. But that's the second purpose of header. But then there is also footer. So the reason why we introduced footer was to make sure that we can do coalescing with the other side. So we can do coalescing. Let's say we have header footer here, payload. And then we have another header footer here, payload. So we want to coalesce with our neighbors. So if you have header, you can coalesce with this guy because we know where the next block is. So now if you have header and then we go to the footer, we can know what this neighbor, like what size of this block is, and then we can coalesce with this block. So we really need this footer so that we can coalesce with the left block. But you can make one observation regarding the header. Header is always needed whether it's allocated or free block. Because if it's allocated block you want to call free, you still need to know the size. So if it's free block, you need to know because you want to coalesce with it potentially, right? So there is probably no way to easily get rid of the header. I mean, there is probably still ways to do some, but this is kind of going to the extremes, right? We don't need to go in this project to those extremes. But footer is a different story, right? So for footer, we only need to have it if the block is free fundamentally, right? So in other words, if the block is allocated, there is a need to know that this block is allocated, but I don't need to know. I mean, if I know that this block is allocated, I don't need footer, right? So potentially, if somehow I know that this block is allocated, because I don't need to know the size of this block. So the moment that I know that this block is allocated, I don't need to know the size. And this is the difference between a footer and a header, right? So that means we can potentially get rid of the footer. So we still need the footer for a free block because we want to support coalescing. And the moment that we know that this block is free, we need to know the size, and therefore still need the footer, right? So I guess that's fine. For a free block, there is not too much waste anyway. The block is free, it's not allocated. So how much space we spend like for footer, header, doesn't really matter too much. I mean, it matters a little bit maybe for smaller blocks, but not in a larger, like in the grand scheme, and from the grand perspective, it doesn't really matter, right? So it's the same deal, right? So for the allocated blocks, it's a different story. So let's say I have a block, I need to allocate 24 bytes. So I need to have a header and footer. This is 8 and 8 bytes. So this is going to give me 40 bytes. But I still cannot do 40 bytes because I need to round up to the multiple of 16. So it's actually going to be 48 bytes. So that's the block that I need to for 24 bytes. So to allocate 24 bytes, I actually need 48 bytes, right? So that's like 50% of utilization, right? Yeah, so now if I allocate, if I can get rid of the footer, I'm gonna get 24 plus 8. So that's going to be 32. That's much better, right? So 32 is much better than 48. And 32 is also close to the original request, right? So it's not like people, it's a much better memory utilization in this case. Yeah, so yeah, I guess that what that observation we can make, right? So in other words, if we allocate blocks like 24 bytes or something like this, which is just 8 bytes larger than a power of 2 number, then so the then sorry, not power of 2 but multiple of 16 number, and it's 8 byte larger, then then it's fine, right? So then we can accommodate this without without the footer better, right? So it's not always going to give an advantage, but in this particular corner cases it will give you an advantage, right? So because you can recycle that space, so you can also use that footer space to feed the payload. So in other words, your payload is becoming larger, right? So now, how can you do that so that coalescence can still work? Because one challenge I have here, okay, if it's a free block, I have a footer. If it's allocated block, I don't have a footer. But how do I know that this block is allocated? Any ideas? Header of what? But I cannot, how can I check the header of the previous one if I don't know the size? So is there any way to solve this problem? Oh. No, but no, I mean, I'm the kind of constant time operation, right? Yeah. So, okay, go ahead. But previous what? Previous block of what? Explicit list? Well, but an explicit list, they can be in completely different order, right? I still need to find this block somewhere, right? So is there any like constant time operation? Yeah, save it in the header, right? So it's actually exactly right. So how do you do that, right? So you're actually gonna say you're gonna in this current block that we are trying to free, right? So this is our current block, and this is the one that we are trying to coalesce with, right? Left, right? What are we going to do is that, remember that we have 4 bits which are not really used for anything. Like, I mean, we recycled 1 bit to keep allocated and free status. So we can recycle another bit, second bit. So to say whether your predecessor, right, so left to the left, is allocated or free. So whenever this guy becomes allocated, it will mark the header of the following block that it's allocated. So whenever this block status changes, it will update the following header. Does it make sense? So now the second bit, which is completely orthogonal to the first bit. So the first bit is allocated free for this current block. But the second bit is allocated free effectively for the left block. So it will be also allocated free, but for the left block, not the current block. And it can be completely different, right? So this one can be allocated, and this can become allocated and free, or vice versa, right? So you just manage this bit independently, right? So that's a completely different bit.
So you're using like the first 2 bits of the header?
Yes, instead of 1 bit, right?
Yeah,
Because anyway, 4 bits are not used. You are 16-byte aligned.
yeah.
So you have a couple of bits for sure, right? So yeah, so this is how you can mark it in this header. You know that this block, your left block, is allocated, so there is no need to go there and check the footer. But if you know that it's free, then you know that this has to have a footer, and the footer will contain a size, and you will be able to call this. So that's the trick that you can use to get rid of footers in allocated blocks. So, and for allocated blocks, it's really important because for allocated blocks, you don't want to waste any space. For free blocks, I guess it's not a big deal, but for allocated blocks, it's really, I mean, you want to get to the bare minimum, right? If you just can keep header and payload, that would be much better than header, payload, and footer.
But without the footer, how would you merge both blocks together?
Well, header gonna say that it's free.
Yeah.
Then it must have the footer. For free blocks, will still have a footer.
Oh, okay.
So only allocated blocks will not have a footer. Yeah, so this is how you can recycle another bit, right? So and how you can fit more stuff there in the header. Yeah, anyway, so this is an optimization you can do, and I don't think it's a hard optimization. Once you reach the segregated list, like that's point, I guess don't start doing it earlier. Well, if you do explicit list, you may try to do that as well. Will probably increase your performance. But I guess it's much easier to do segregated list from explicit list than this, right? But again, it's up to you. I guess the order. I mean, you can even do that. I guess in implicit list, but that is probably not worthwhile, right? Because that's not something that will give a significant performance boost, right? Like segregated list will give a significant performance boost, and this one will give like additional points when to get like 100%, right? So I think in the past I tried to implement it. I implemented segregated list, and I also implemented this optimization. So my segregated list was 92% or something like this. I think it was first fit. Yeah, so you can do best fit with I guess 95% score. It's still not 100%. So if you implement this, that even I think first fit will give you 100%. And best fit within segregated list also should be fine, right? Yeah, I think yeah, so it's up to you to decide whether to use best fit or first fit for segregated within the segregated list class. Because best fit can be also considered there. But again, you need this optimization to reduce internal fragmentation. Okay. Any questions about this? How many of you are already working on segregated list? Explicit list? Okay. Yeah, so I guess once you are done with explicit list, you will switch to segregated list, hopefully, right? And then you can implement, and then as the last step, you can implement that. Okay. So last time we talked about multi-level page tables, and I think that's the last picture we looked at last time. And just to recall, that we have the virtual page offset that is directly to transfer to physical page offset, and then virtual address can further be split into different page table level components. So by the way, why is it possible to split into different page level components like this, right? So why we can do that? So we previously had a similar question for page offset, right? Why we can just take page offset, because it was a power of 2 number, right? So we realized then, okay, then we can use a certain number of bits just to directly extract page offset. So why is it still working for different levels in the page level, in the page table? Well, again, because the page size is a power of 2 number, right? And that means, and the entry size is power of 2 number. That means the number of entries in each page page level, right, is going to be a power of 2 number. So because a power of 2 number divided by a power of 2 number is still a power of 2 number, right? And therefore, you can still continue extracting bits like this. So again, the reason for that is because the page size was a power of 2 number. And because the entry size is also, right, power of 2 number, 4 or 8 bytes or 16 bytes, whatever it is. So that means we can extract it directly. We can go to so the level 1 is going to correspond to the upper bits, and level K is going to correspond to lower bits. I mean, if we're not taking offset into account. So, and the reason for that is that at the higher levels, like level 1, well, I say it higher level, but number is smaller, right? So it's a little bit confusing, right? But the higher level in terms of, like, if you consider it as a tree, right? So that's the upper level of the tree, and or level 1 here. That means it should be like, it's really dealing with like large numbers, right? So it's not dealing with individual pages. It's like, for example, if it's a 32-bit processor and we have 2 levels, so level 1 in that case will deal with megabytes rather than kilobytes, right? So it will refer to like 4 megabytes of the second level, another 4 megabytes of the second level. So you have 1024 entries in the first level by 4 megabytes, 4 gigabytes, right? So that's the maximum virtual address size there. But you know, so you're dealing at much coarse-grained level, right? So with the second level, it's more fine-grained. So, and then when you look at the virtual address, it's the same deal, right? So you look at the upper bits, it's like it corresponds to the upper layers, right, of the page table. So also to keep in mind that the page table base register will contain an address to the level 1 page table. So and level 1 page table is typically just one page itself, right? So that means it's like a root of this tree. It's just one page, right? And then it points to, let's say, 1024 other level entries, right? And so on, right? Yeah, so okay. Just recall that we have this abbreviations. I think we talked about this in the past: TLB index, TLB tag, TLBI, and TLBT. Virtual page offset, virtual page number. Also, something new that we will use cache cache offset. This is a byte offset within a cache line, cache index, cache tag. Yeah, so let's consider an example of some memory system which with 14-bit virtual addresses, 12-bit physical addresses, and the page size of 64 bytes. So again, this is given just by a specific system. Like, I mean, in x86 we have 4 kilobyte pages. Like in x86 64 we have, let's say, 4 kilobyte pages, and we have 48-bit virtual addresses and 52-bit physical addresses, right? As an example. Some maybe later revisions have more than 48-bit virtual addresses, but it certainly cannot be more than 64-bit, but I think it's currently 57, I think 57-bit. Yeah, so so anyway, this is given by the given by specific architecture. So if you have 64 bytes, I guess that's a little too small for a real system, right? But for the purpose of this example, that will be fine. And it's still a power of 2 number. So for 64 bytes, how many bits do we need to have for the offset? We need to have 6 bits. 2 to the power of 6 is 64. So now for virtual page number, if you have 14-bit virtual addresses and 6-bit page size, right? Well, so page offset, sorry, 6-bit page offset. So what is the virtual page number? How many bits do we have? What in bit virtual address minus 6, right, offset? So it's going to be 8-bit. Yeah, so 8-bit virtual page number. So that means our page table should have entries from 0 to 255. Because 2 to the power of 8 is 256. So we should have 0 to 255 entries. Okay, and then physical page number is a 12-bit address. So the page offset is going to be the same, of course, but the page number can be entirely different. Again, as I said, virtual addresses and physical addresses can be entirely different. They don't have to be the same of the same length, even though maybe for 32-bit processor used to be the case, like 32-bit virtual addresses and 32-bit physical addresses. Even that was at some point later extended to higher physical addresses than 32-bit. But for x86 64, that's certainly the case. We have 52-bit, I think, physical addresses, and in practice actually less than this. I think it's 39 on my computer. And then you have virtual addresses which can be 48-bit or 57-bit, again, depending on the CPU revision. Okay, so so again, these numbers are entirely different, and they just, so only the page offset is going to be the same in both cases. So let's say we have a TLB. So if you have 16 entries, right? So what does it mean four-way set associative? Well, if you have 16 entries, and let's say TLB index is a 2-bit number, right? So the one that, remember that TLB index is a part of your virtual page number. We looked at this previously. So you split your virtual page number into 2 components, TLB index and TLB tag. So in index determines the corresponding TLB location, right? Where the corresponding set in TLB that you're going to modify. So it's 2-bit, it's 4 sets that you have, right? So that means it's going to go from 0 to 3, and you're going to choose the corresponding set. But then in each set, you have effectively have 4 columns. So you're going to keep 4 different tags for each set. So in total, you have 16 entries then, right? So you have 4 by 4, 16. So and this is why you can this is why it's called four-way sets associative, right? So because you can have because this is how we split it, right? And let's say we have the same TLB index, we have 4 columns, so we can have 4 different tags there, right? So we can store 4 different tags there. Hopefully, most of the time your addresses are local, and therefore TLB index is something that you need to worry about most of the time, right? So you want to make sure that they're in different sets. But TLB tag occasionally going to have some high addresses, like which may just be like maybe you jump into some C function or jump into something else. So you want to have a different way, have an alternative way to store a second tag or third tag or fourth tag that corresponds to the same set. So it may be entirely different address, just happen to occupy the same index. Yeah, so given if you have a locality, hopefully TLB index will handle most of the time that stuff, right? Because you have different sets, but occasionally because you have collisions, you still have to maintain multiple tags. So in the terms of the page table, we have 16 entries, right? So let's show 16 entries, but and remember that the total number of entries is high, it's 256, because it's 8-bit number, 2 to the power of 8 is 256. So that means we have to go from 0 to 255 potentially. So it's just an example of the page table. And by the way, this is just a single level page table here for simplicity. So you have a corresponding virtual page number that has a corresponding physical page number, and then you have whether it's valid or not valid, right? And in addition to this, you have other bits like read-only bit, supervisor bit, and so on, right? So yeah, just to kind of connect things together, right? So recall that if you have the page table, and this is how many entries we need. Then we have system memory cache. So in the memory cache, we have page offset and page number, right? So perhaps memory cache is designed such that it will also take into account your physical page size. So it will split so-called cache tag and cache index and cache offset in like using that maybe information. It doesn't have to be, but maybe for some make the hardware easier, implementation easier. You wanna probably don't exceed cache index, maybe the page size boundary, right? So let's say we have cache with 16 lines, and each line is a 4-byte line, right? So that means each line, so I'm gonna keep 4 bytes. So whenever I'm gonna access memory, whenever cache is gonna access memory, it's gonna read the entire 4 bytes. Even if you're just reading 1 byte in your program, the cache, the underlying cache will have to bring 4 bytes. So now, what does that like, I mean, in practice, what does that mean, right? So if you consider, let's say, x86 64 architecture, we have 64-byte cache line there, right? And CPU word size is 8-byte. So again, don't confuse the CPU word size with the actual with how much memory will be accessed by the cache. So it can be actually larger, right? So it can even be smaller, right? It depends on what architecture it is. In case of x86, we will have 64-byte cache lines, and even though you have CPU word size of 8 bytes, that means even if you are modifying like just 8 bytes, you still want to bring the entire cache line whenever you read the corresponding 8-byte block. So you will you read the entire 64-byte block. It will contain multiple 8-byte words, but you will do that you know, at every single iteration, right? So the cache line, whenever you have a cache miss. So this is why having locality is important here, because we may potentially be accessing. I mean, we're reading 64 bytes. We're hopefully going to be bringing more like words later, right? So that are close by. So by the way, just putting that example aside and putting maybe x86 example aside, what is the why is the alignment important in terms of cache? Like maybe consider that in terms of cache. There might be different reasons why we want to align data structure fields, but let's say why do we need to align 8-byte words in x86 64 on 8-byte boundary? Okay, go ahead.
Was it stored, eight bytes each? So it's easier to-
Well, but what is easier here, right? So can you elaborate on this? What is easier here? I mean, some architectures, it will not be even supported. It will generate an exception or trap, right? So in x86, it's going to be, it's not going to generate an exception, but it will be slow. So why is that? Can you connect that kind of answer to cache line? So if you have 64-byte cache line, like put in that example set, 64-byte cache line in x86, and you want to read 8 bytes, and let's say it's not aligned at 8-byte boundary, then what can happen? Okay, good. Yeah, so then it may potentially be line in 2 different cache lines. So if you align, it will never happen. If you align at the 8-byte boundary, that's always going to stay in the same cache line. But it's this cache line or another cache line. But if it's not aligned, then you will potentially occupy 2 cache lines, and that will become more expensive. And some architectures may say, okay, you're trying to modify a word across different cache lines. I'm not even supporting this. Let me generate a trap. So yeah, so this is something to keep in mind. Yeah, so okay, let's go back to our example. In our example, again, it's a very simple system. It's 4-byte block size. So that means it will bring entire 4 bytes, even if we just accessing 1 byte of memory. It has 16 lines, right? So, okay, so this is, remember that the cache is physically addressed. It's not, we already have finished the virtual to physical translation at this point. It's also handled pretty much transparently by the CPU. There is no translation here, right? So it's pretty much directly mapped, right? So again, when we look at the cache offset, it's some information from the physical address that we will disregard when we try to locate the cache entry. Because yeah, that just means an offset within this 4-byte block. You can fit 4 bytes, you know, that means it's 2 to the power of 2 is 4 bytes, right? So yeah, so that offset will come later, right? So once I need to extract the corresponding byte. So, but to determine the cache entry, I need to use the cache index. So that will be how many bits? It's going to be 4 bits. So in 4 bits will correspond 2 to the power of 4, 16. So we have 16 entries in cache from 0 to F. So we will determine the corresponding place in cache by using cache index, and then we'll have cache tag. So again, we need to store the tag component. This is a physical page number in our case, so that we will know, okay, this is the page that's this page or that page, right? So that we because we will occasionally have some collisions. Again, system cache, of course, sooner or later we'll have to evict some entries and put some other entries, right? So because multiple pages will be competing for the same spot, right? But if you have a good locality, hopefully it's not going to be that frequent. And even if that happens, I guess to some extent it's a less of a concern in terms of the cache compared to TLB. Yeah, I guess in TLB, especially if you consider multi-level page table with TLB. So why is that? Why is TLB can be problematic with multi-level page tables? Like, I mean, why TLB TLB miss is even more problematic when we have multi-level page table. Any ideas? Oh, by the way, is it again cold today? Is it possible to make it warmer? I think there is some. Yeah, I think we can change the temperature. Yeah, I mean, I guess we should check somehow they put it really cold here, right? Okay. So why is that? So what was the question? So okay, why is it a problem for multi-level page table to have a TLB miss? Well, if you have a TLB miss, what will effectively happen is that you need to go read one level, then another level, then another level, right? So it's multi-level. You have to transfer not just one memory access that you're gonna have, but multiple memory accesses to get this corresponding mapping. And that is a problem, right? So this cache, if we have TLB miss, okay, that's bad, but I just need to have one memory access after this. With TLB, it can be really multiple memory accesses. So therefore, having more tags in TLB in the same spot is even more important than here. So again, this is nothing probably special here, just an example. Some of these cache entries are valid, some are not. And then, we can see that for each entry, we have byte components, byte 0, byte 1, byte 2, and byte 3. This is where the data is stored. So let's consider an example of address translation and see how things are going to work from the virtual address to the corresponding cache entry. Yeah, so let's see. So we have 3D4, right? So 3D4. That's our virtual address. Maybe that's something that we found in some pointer and we need to translate it. So how the CPU will translate it? Okay, 3D4, that's four. What is 4? 4 is 0, 1, 0, 0, right? So D is 0. Sorry, not 0. 1, 1, 1, 0, 1, I think, right? 1, 1, 0, 1. Yes, yeah, that's correct. Yeah, so then it's 0, 0, 1, 1, right? For 3. So this is just hexadecimal and binary, right? So now we have to a virtual page offset. How many bits we had in virtual page offset? We had 6 bits, right? So it's a 64 byte page in our example. So we're gonna take these bits. This is the virtual page offset. Just give me a second. Okay, and then we have our virtual page number. This is this component, right? So by the way, we have some extra bits in front, right? Because it's 14-bit iris, but we will add it in a moment. So yeah, so now how do we decide? Okay, TLB index. So what is the TLB index and TLB tag? That's part of the virtual page number that we have discussed, right? Because TLB deals with the page numbers; it doesn't care about offsets. So TLB index, we decided that it's we have 16 sets, right? So we have and four tags per each. Well, we have four. We have 16 entries. We have 4 sets with 4 tags in each set, right? So that means we have two bits for TLB index, so that we have 4 sets. 2 to the power of 2 is 4. So this is going to be TLB index. And TLB tag is going to be the remaining bits. So how many remaining bits do we have? So you have 8 bits for the virtual page number, minus 2 bits for TLB index. We should have 6 bits. So we have 4 bits. That's why we have to put a couple of zeros in front, right? So it's actually 2 more bits, right? So this is going to be TLB tag. Yeah, so what is the virtual page number here? If the virtual page number is 00001111, right? So it's basically 1111. That corresponds to F. So the virtual page number is F. So TLB index is 3, right? So and then TLB tag is also 3, right? 11 is also 3. So let's say we found the corresponding TLB entry. There is a TLB hit. We found that the tag. So we use the index to find the entry. We compare the tag matches. So we have TLB hit. At that point, the TLB will contain the physical page number. So and therefore we don't have any page fault. We're gonna go to we're gonna go and read the corresponding page. So at that point, let's say we retrieve the page number that's going to be stored in TLB. We retrieve 0D, right, as an example. So again, that's just an example. It can be any number for the purpose of this example, whatever the corresponding mapping it was, right? So let's say that was in this map and we had 0D for the physical page number. So now what do we do with the physical page? Again, physical page can be split into components. So we will have physical page offset, which is the same, right? So let me. Physical page offset going to come from the virtual page offset. That comes directly 0, 1, 0, 1, 0, 0, right? So that's our physical page offset. And then physical page number we have just retrieved from TLB. This is 0D, and D is what? So what is D? That is 1, 1, 0, 1, right? Am I correct? Yeah, I think 1, 1, 0, 1. Yeah, so that is our physical page number. But actually it's more because, you know, remember that the physical page number is 12 bits, so we have to put, sorry, not physical page number, physical page number is, we have 12 bits physical page address, sorry, physical address is 12 bit, out of which we have 6 bits for the page offset and another 6 bits for the page number. So the page number is 6 bit, right? So therefore it's also we have 0, 0 in front. 0, 0, 1, 1, 0, 1. That's our physical page number. So, and that will also in our example will correspond to cache tag. So now the offset, so cache already kind of works with much smaller units than pages, right? So cache will, again, in the case of x86, we have 64 bytes and page 4 kilobytes. In this example, we have like 4-byte entries and 64-byte page, right? So cache is typically smaller, right? And then within this page, we will effectively split the cache index. We will use this 4 bits. And because it's 4-byte entries, we don't care about last 2 bits. So this is the offset within the corresponding for the corresponding cache entry. So we have 4 bits here. So the offset is 0. So that means we care about the byte 0 in the corresponding cache entry. Cache index, the one that will determine where the cache entry is 5, because it's 101, right? And then cache tag is D, which corresponds to the physical page number in our example. And yeah, so let's say we have a hit, cache hit, and then directly extract byte 0, which is 36, right? Just again, just an example that the data, the corresponding data is 36. So another example, you have TLB miss. You know, again, it's just, I'm not going to go through this example again, right? So that's just the TLB miss. That means we will not have, let's say, page fault yet because we have a page table entry, but we just need to bring it from memory, and then eventually we will retrieve the corresponding physical page number. So maybe once we retrieve the physical page number, we try to access that memory, and again, we will try to access cache first. So then what will happen? And let's say we also have a miss, cache miss. At that point, it will go and retrieve the corresponding byte from memory. So the cache doesn't have it, it has to go to memory and read it. Oh, sorry. So the next thing we will talk about is memory mapping. So in terms of like, remember that when we talked about virtual memory, we also talked about secondary storage, that virtual memory you know, can often be often has to be backed by secondary storage. So you don't necessarily have to fit everything in physical memory, but periodically you're going to go to your disk and bring the corresponding pages from disk. So the process is kind of known as memory mapping, right? So in the area, the virtual memory area can be backed like by regular file. Let's say I have an executable file, has the text section, data section, whatever it is, right? So that will come from directly from the file. from that executable file. So you just mark that, okay, that in that file, I have the corresponding page. So you have a page fault, and the page fault handler goes and grabs that page and brings it to main memory, and you execute the program, right? So that's backed by a specific file. But you can also have an anonymous file. So it's not can be backed by, cannot be like, I mean, it will not be backed by anything. And one example is your memory allocator. So if you look at the memlib, I think it's doing memory map call and map, and what will happen there, I think it will specify anonymous mapping. So it's just basically, it means it wants to allocate memory, right? It asks the OS to provide pages so that it can use for your heap. So the first, and in fact, that's what happens. That they reserve, I think, a large area in the, if you look at the memlib-c, they reserve large area, but it's not actually allocated in your physical memory until you start using it. So the first fault will allocate a physical page full of zeros, right? So it's going to be, so the first time you access the corresponding page in your memory allocator, after you have done mems brk. So mems brk is kind of barrier, but it's really kind of artificial barrier there, to be honest. But it's just to kind of keep track of how much memory you have used for the benchmark. Yeah, so because there is already area that is kind of pre-allocated, right? But then it will not actually be used. So it will not actually bring any physical pages until you start using it. So this is the first fault. The first time you're going to write to that page, it will cause a page fault in the OS. And then there will be a corresponding physical memory allocated for that page. So sometimes it's called lazy allocation, or, you know, so you're not proactively allocating, you're just reserving the corresponding page table entry and saying that this memory is valid. You know, it just exists on the disk, but doesn't exist in physical memory yet. So then the OS will allocate this corresponding region when you have the first page fault. So, and then, you know, once you write something to that page, it will become just like anything else you have so far. So the process of writing to the page is sometimes known as dirtying, right? So you have a so-called dirty bit, so you make this page dirty, so to say, right? So so why, by the way, why do you need the dirty bit? Okay. Yeah, so but can it help us somehow for the secondary storage? So if the data was not written, then perhaps later on, if you need to evict the page, we don't need to write that data if it was not modified. So this is the one example why the dirty bit can be useful. Yeah, so you know, dirty pages on like, I mean, dirty pages are going to be copied back and forth to between memory and swap area, because you know, the moment that we modified it, we want to also the swap area to reflect that change, because if it, you know, if it's not reflecting the change, we will lose it, right? So whenever we evict the page, if it's the page is marked as dirty, we have to also write it to the swap file. If the page is not dirty, the swap file you know, still has that valid copy, so there is no need to write it. So how do we do sharing? So let's say process one has a mapping and it want to map a shared object that will also be shared by process two. I mean, it can also allocate its own memory. It can have its own physical memory mapping, but you know, one specific place that it will have shared memory object, which is also going to be used by process two. So in process two can map the shared object in a completely different place. So it doesn't, I mean, the physical address for the shared object is going to be the same, but the virtual address in each process is going to be different. So again, why is it useful? Well, when, for example, we have libc, C library, the standard C library, multiple processes will use it. Almost every single process will use it. So that means, I mean, it's good to share that stuff if you, at least as much as you can, right? I mean, certain things you cannot share, like if there is some data related to this process, you cannot share that. But code, I mean, certainly can be shared, or read-only data can be shared. Yeah, so, but remember that I think I mentioned in the past, there is a position-independent code which allows you to map it to different locations in memory. But again, virtual memory addresses in different processes, even though they map in the same physical memory, they don't have to be the same. In fact, even within one process, we can have multiple mappings to the same physical memory. So multiple virtual addresses can correspond to the same physical address, potentially. I mean, it's not always used, but sometimes you want to have that behavior. So another thing to note is how we can implement things like copy on write. So let's say we have two processes, right? So and there is some private area, maybe there is some data which we don't know whether it's going to be read-only data or something that's going to be modified later. So we will want to mark it such that if it's modified, it will be it will be copied. So in other words, both processes will start with exactly the same copy, but once some of this process start changing something, right? Then they're going to be corresponding exception or trap in OS. It will create a separate private copy for that process, and will change the corresponding page table mappings. So how do you do that? How do you implement this? How can we generate a page fault? Any ideas? I mean, the answer is on the slide already, to be honest. But yeah, how can we generate it? Yeah, go. Well, but what is generating that? What is triggering page fault? So what will trigger page fault here? So what kind of bits should I set in the page table to generate a page fault? Yeah, so but what flag? What is that flag? So I'm right into this page and I want to generate a page fault. Well, any guesses? I mean, the answer is literally on the screen, right? So you have to have the mark read-only bit. Yeah, so you have this read-only permission bit. So you try to write to this page. It's marked as read-only. It generates a trap. You execute a page fault handler, and then you're gonna create a private copy here, right? So of that page. So it's not a fatal error, right? So it's kind of by design. You want to generate a read-only. You want to have this read-only mapping so that you can create this private copy on demand. So once you create a private copy, this read-only flag will be gone in the new page table. But that's something that you will need to modify. Yeah. So why is the copy on write useful? Like specifically in terms of fork. So what do we do in fork? So what does fork do? Okay, there's some stuff you have to know, right? So what? Okay, go on. Yes. Yeah, so it creates a copy of a process. But you know, it's from the user perspective, it creates a copy of a process, but doesn't have to create a copy of the process right away. No, it can also use the copy on write technique. So it can mark the stuff and say, okay, lazily, as the user will change that memory, lazily I will allocate new pages as needed, right? So, but right now I'm gonna keep the same exact copy like as was in parent, and once it's something that changes, then parent and child will diverge, right? But until that point, they will use the same page. And why is it specifically good for fork? Why do we want to avoid copying? So what will happen typically after fork? Like when you run an executable file. So you want to create a fork, you want to create a process, and then you want to substitute the image. So basically, you want to substitute the entire virtual address space with an entirely different address space with an executable file, right? So it means having that implementation in fork based on copy and write eliminates this overhead. So because the likelihood that this write will ever happen is almost zero, because you're going to actually go and do exec. I mean, unless you want to use the fork for as a child process, like in a browser, like you have a separate tab, right? But other than this, let's say if you have fork and after this followed by exec, it's actually very crucial to have that optimization based on copy and write, because you will never make a copy of this process. Because it will never diverge even from the parent process. I mean, it will diverge by a little bit, but that's, you know, maybe one page or something like this, right? It's not a big overhead. But you know, other than this, it will just erase the existing address space and create a new one. And at that point, we can forget about the parent process altogether, right? Yeah. So yeah, this is just to kind of reiterate what will happen when we have copy and write. So we mark the read-only region. We have a trap. We generated a trap. In the trap handler, we moved the corresponding area, right? So we created a new read-writable page. So now when we create a copy, that can be writable page. It don't have to be. It doesn't have to be read-only anymore. You know, and this is how you defer copying as long as possible. And deferring is very crucial for forking, right? So because very likely you don't even need copying eventually, but you don't know that for sure until you call exec.